Hello everybody, we are in the last lecture of this counter topic. So, in earlier lectures we have seen how to design counter with different modulo numbers using asynchronous reset and preset. And in that we have seen that there is a small glitch that is possible because of the reset precedes going to the next state, and an asynchronous reset ensures all 0 or a preset value appearing in the same clock cycle. So, in this particular class we shall see how synchronous counter with different modulo number can be designed, and that design can be considered as a synthesis sequential logic circuit design problem. And we shall see that those kind of glitch will not occur. It does not require to go to next state. Straight away the next valid state in the sequence as per the modulo number, if n unique states are there, those n unique states will be appearing one after another. And we shall also look at some specific application other than the ones that we have seen before. Okay. So, we start with an example where we are taking mod 6 counter. Okay. So, in the mod 6 counter we are having 6 unique states, and we are considering a up counter for this discussion, and this counter has got the 6 states 0 0 0, 0 0 1, the one that you can see 0 1 0, 0 1 1, 1 0 0 and 1 0 1. After that again it goes to 0 0 0. Okay. And we considered of all the flip flops JK to be the one by which we would like to design it, right. So, for JK flip flop, since it is a synthesis problem, for design we shall refer to its excitation table. So, this is the excitation table, right. So, if the flip flop current state is 0 and next state is also 0, okay, as per this transition diagram, then at the input what should be present? 0 cross. 0 1, 1 cross should be present, 1 0 cross 1 should be present, and 1 1 cross 0 should be present. Cross 0 means one of 0 0 or 1 0, either way it is fine. Okay. One of these two combination, either 0 0 or 1 0, that will ensure 1 1 transition, 1 to 1 transition for JK flip flop. Okay. So, this we already know from our earlier discussion on flip flop. Okay. Then we shall follow the standard synthesis process. So, once we have this state transition diagram, we shall go to the state table and we shall use the excitation table for getting different input combinations for different states. So, 0 0 0 is the initial state over here, like, right. So, for that the next state is 0 0 1. Okay. So, what will be the corresponding input for Cn changing to Cn plus 1, 0 cross from here. Okay. Bn is also changing to Bn plus 1, is that is 0 to 0. So, 0 cross, and An changing from 0 to 1. So, it is 0 to 1 transition. So, 1 cross. Okay. Is it clear? We are just recollecting and what we had done before in simple synthesis example in earlier classes. So, this is the first row. Similarly, the second row, after 0 0 1 it has to go to 0 1 0. Okay. So, this is 0 1 0 and corresponding transition 0 to 0, 0 cross, 0 to 1, 1 cross, okay, and 1 to 0, 1 to 0 you can see over here 1 to 0 cross 1. Is it clear? Second row is also clear. Okay. So, third row 0 1 0 to 0 1 1. So, 0 0 0 cross, 1 to 1, 1 to 1 this line cross 0, and then 0 to 1 1 cross. Okay. 0 to 1 1 cross. Okay. So, with this if you proceed we will come to 1 0 1, right. Now, after 1 0 1 in earlier design that was a modulo 8 counter, standard 8 counter, and it was going to 1 1 0 and we are doing a asynchronous reset. so that 110 and 000 were occurring in the same clock cycle. Okay, for a very small duration 110 was there. Now, in this design, after 101 we are going straight away to 000. Okay, here it should be 0, right? It should be 0. Okay, right? So 1 to 0, it should be cross 1. So that is your cross 1. Okay, 0 to 0. So this is your 0 cross, and 1 to 0. 1 to 0. So this is your cross 1. Is it clear? So this was a typo error. Okay. Is it fine? 1 to 0, right? That is your, I am doing it once more again. So this will be 0. Okay. 1 to 0, this is your transition cross 1. So that is your cross 1. 0 to 0, 0 to 0, this is your 0 cross, and 1 to 0, 1 to 0 again cross 1. So this is cross 1. Is it clear? So from 1 0 we are directly going to 0 0 0, right? So this is the thing that we are doing in designing a modulo 6 counter using standard synthesis design problem. Okay, the way we solve a sequential logic circuit design problem. Okay. Next, what is the next step? So next step is from those inputs, okay, that state table we are writing the equation, corresponding equation for individual inputs. Okay. So JC, KC, JB and KB, right, and we have already noted in the previous case that is J and K. If you look at the previous one, okay. So 1 cross 1, 1 cross 1 and so on. So that is the thing that has been reproduced here, and rest of the things are taken from here to the next this Carnot map based simplification. So all of them are this 1 or cross. So we can consider all of them as 1, then it becomes the simplest possible. So that way you can consider each one of them as 1. Okay. So in the corresponding table you can understand that this is 1 cross, okay, then 1 cross, and these two are 1 1 0 and 1 1 1, we can consider them as cross. So all of them can be put together. So this is your 1, fine. For other cases we are just substituting the values, taking the values from those columns, and remember this 1 1 0 and 1 1 1, those were not there. Those last two possible with 3 flip flops, 8 possible states are there. So 1 1 0 and 1 1 we didn't consider, right? It will not, it is not a valid state, isn't it? So we consider for those two cases cross cross. Okay. So this is cross cross. That means it doesn't matter, because it is supposed, it is considered that it will never go to those states. Okay. So it is initialized with one of the valid states. This counter is initialized with one of the valid state. Later on we shall see if it is not the case, then what will happen. So that we shall take up little later. So over here, okay. So accordingly we do not have any compulsion of if there was a 1 or some such thing 0, considering treating it accordingly. Okay. Now we can consider them as don't care, and depending on that we will get a minimized circuit. Okay. So these are the corresponding equation, right, and once these equations are obtained, from there we can get the circuit, right. Is it clear? Okay. So this is the standard sequential synthesis logic synthesis problem. Okay. We look at how this particular circuit, behaves when 1 0 1 comes here, okay, over here, and then with the clock trigger, how it goes to 0 0 0 without any glitch or so, right. So 1 0 1. So this is 1, right, and this is at 0 and this is at 1, right. and when this is 1 and this is 0 and this is 1. Okay. So, what are the corresponding inputs of this flip flop? So, JAK is always 1, that we have noted, is not it? And this JB is, we have found from the previous Carnot map based simplification, is Cn bar An. So, accordingly the circuit has been drawn. Okay. So, Cn bar, because it is 0, so together it is 0. Okay. And what is An? An is 1, 1. So, this is 0, 1, fine. Okay. What about JC, KC? So, JC is Bn, An, right. So, An is 1, but Bn is 0. So, this input is 0, right. And what about KC? KC is An, An is coming over, this is 1, right. So, for A flip flop you have got 1, 1, for B flip flop you have got 0, 1 at the input, and for C flip flop you have got 0, 1 at the input, right. Now, when the clock trigger comes, what will happen? Okay. Now, when the clock trigger comes, you will have 1, 1, it toggles, so it will become 0, from 1 to, it will go to 0, 0, 1, okay. For the JK flip flop 0, 1, if it is the input, then it will be 0 only, right. And here also it is 0, so it will be 0 only. So, with the clock edge, all of them go to 0, 0, 0. Unlike the asynchronous reset based modulo 6 counter, where we had got 1, 1, 0, and at that time with this value it was getting reset, and the output was obtained, I mean the next state was obtained as 0, 0, 0, okay, for longer duration of the time. Is it fine? Right? And this is the decoding of the counter. So, this part is understood, right. Now, we look into the case for the two states 1, 1, 0 and 1, 1, 1, which we did not actually consider in our design process, right. So, in this particular case, this is the circuit diagram we are having. Suppose it is initialized with, or because of some noise or some surge, it goes to one of those two states. Okay. So, if it goes to 1, 1, 1, 1, 1, 1, and then you can consider the calculate the input for each of the flip flops, right, and with the next clock trigger you can see that it is coming to 0, 0, 0, and then with clocking it will keep circulating like this as per this state transition diagram, and a mod 6 counter will be there, okay, after that. And had it been initialized, or it had it be gone to the other invalid state, which is 1, 1, 0, with a clock trigger it would have been come to 1, 1, 1 and then to 0, 0, 0. Okay. So, this is what happens for this particular circuit, but this is happened just like that. But there could have been another, there could have been other possible cases where if it is 1, 1, 0 with clocking, right, it remains at 1, 1, 0 only, right. With 1, 1, 1, it is remaining at 1, 1, 1, or 1, 1, 0, it is going to 1, 1, 1, or with from 1, 1, 1, it is coming back to 1, 1, 0. That means it is getting trapped into the invalid states only, and it is never coming to one of the valid states. Okay. That also could have been a possibility, okay, because we got this way that it is not getting trapped, okay, but it was not by design. Not by design, right. We just see that it has happened in that manner, but in another design there remains a possibility that it could be locked in one of these cases, or if there is a modulo 5 counter, there could be 3 invalid states, it could be locked in one of those 3 states or so, or keep circulating there. Okay. So, this is something which we should think of avoiding in a counter design, right. So, for that what you need to do? We need to explicitly, okay, consider them in the design process, right. And how you can consider? So, there could be multiple ways. So, in this example what we see is that for one of the for any of these invalid states, if it goes 1, 1, 0 or 1, 1, 1, okay, the next clock trigger it comes to one of the valid state, which is the 0, 0, 0. Okay. After that it will continue to count 6 the way it was designed, it is already designed, right. So, for this then these two unused state which we did not consider in the earlier design, and there was a do not care option in the Carnot map based simplification of the design equation. So, they now get into picture, right. So, 1 1 0 we are getting 0 0 0 and corresponding C, B, A flip flop inputs are like this, and 1 1 1 it is also 0 0 0 and these are the corresponding inputs, okay, from the JK flip flop excitation table, right. Now, other than those 6, these 2 also are getting considered, right. So, to explicitly get around or avoid the getting trapped into the what is that called unused states, right. So, now the design equation becomes a little bit more complex in the sense now this earlier these 2 cases it was always do not care. So, we had greater flexibility in deciding the equations. So, corresponding equations have now become like this, right. So, you can see that earlier these equations, right, for example, J A, J was all 1, J was 1 because this was a do not care, right. Now, there is a 0 over here, you cannot treat this as a 1. So, accordingly it has become C n bar plus B n. So, we are sacrificing some of this design flexibility and hardware becoming a little bit more complex, but the benefit is that there is no lockout kind of situation. So, no getting trapped into the unused state. So, that is what you can see that this was the earlier circuit, and now with those design equations for inputs, this is the modified circuit. So, where the invalid states are going to valid 0 0 0 at next clock trigger, and this is what is expected also, isn't it, right, fine. So, now let us look at another aspect of the design. So, we had been discussing this up counter, again similarly down counter is possible, and it is also possible that we can have these counting states. They need not be regular in the sense that it is increasing always the number is increasing one after another, by a value of 1 or getting decremented by 1, right. So, it is not necessary that it need to be like that. We just need as many number of unique states, and that can also be considered in the design process, right. So, here is one such modulo 4 counter where the numbers are not 0 0 0 1 1 0 1 1 again 0 0, it is not like that. What is it? 0 0 after that 1 0, then 1 1 0 1 and then 0 0. One good thing about it, what you can see here, that only one bit is changing, which could be useful in some consideration in some cases, right. So, between two counting states one after another, only one bit is changing its value, right. But otherwise the significance, the corresponding decimal equivalent 0, 2, 3, 1 again 0. So, in that sense it is irregular. So, it is not 0, 1, 2, 3, 0 or the down count the way I have seen that 3, 2, 1, 0 and again 3 is not like that, right. So, that sense. And what else is there in this particular example? So, we had used JK flip flop, right, earlier. Now, we are considering D flip flop. So, with D flip flop also you can design counter. So, let us see how. Since it is D flip flop, so D flip flop excitation table will be put to use. So, this is 0 to 0, then 0 should be input, 0 1, 1 should be at the input, 1 0, 0 should be at the input, and 1 1, 1 should be at the input. Is it fine? So, this is the way the excitation table of D flip flop we have seen in earlier classes related to flip flop, right. So, now 0 0 to 1 0, 0 0 to 1 0, okay. Then 0 1, if it is 0 1, then it goes to 0 0, if it is 1 0, it goes to 1 1, and if it is 1 1, it goes to 0 1. Okay. So, you need to take note of this thing, that it is not coming one after another 0 0 to 0 1 and it is just incrementing in that manner. So, you need to be careful about this aspect in the design process, not to make mistake when we map it to Karnaugh map, okay, right. And then D flip flop is whatever is the next value, that is the input, okay. So, 1 0 1 0, so 1 0 1 0, so 0 0 1 1, so 0 0 1 1, okay. So, accordingly you have got your this Karnaugh map entry, and these are the equations, okay. Is it fine? Right. So, with these equations we can get the circuit made, right, and this circuit will behave like a mod 4 counter with counting states 0 0 1 0 1 1 0 1 again 0 0. Is it fine? Right. So, these are example with mod 4, it can be done for mod 8, mod 6, mod 4, 5, whatever, right. And whenever we are using modular number which is not integer power of 2 with flip flops that can have some invalid states, unused states, it is better that we take care of it by putting them into the design consideration to avoid any kind of locking. Okay. Now, we had seen counters getting used for of course, the counting number of pulses and all, and then digital clock where seconds, minutes and hours, this count was getting incremented using different kind of counters. So, mod 6, mod 10 together giving seconds and also 2 minutes, and then mod 12 for the hour count. All those things we have seen before, okay, as use of counter. This is the standard, those are the standard uses, right. And there can be few other uses of counter where we can see that counter can be used for in this example sequence generator, okay. So, how is it? Okay. So, the counter sequence generator we had seen before using shift register, mostly shift register and linear feedback shift register also, right, and that is also a version of shift register. And here in as a counter, so what we do, say we are looking for a 8-bit long sequence, okay, which gets repeated, right. So, we are then having a mod 8 counter with us, okay. So, this can be extended to 16-bit long sequence. So, then we will be having a mod 16 counter. So, 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1 and then again 0 0 0 is coming, right. And for each of this count, as the clocking occurs, so whatever the sequence output, sequence generator as a sequence generator, the output that you consider in the right hand side, okay. So, this say we want to generate 0 1 0 0 1 1 0 1 again 0 0 0 1 0 0 1 1 0 1, that is repetitively. So, now this becomes a combinatorial logic circuit problem. So, if the count is 0 0 0 the counting state, the output will be 0. If the counting state is 0 0 1, output will be 1, 0 1 0, output will be 0, and this counter is keep repeating itself, okay. So, this 0 will again come over here when 0 0 0 comes, this 1 will come again when the counting state is 0 0 1. So, this is the way you map it, right. So, we have to ensure a logical connection between y and CBA, right. So, CBA is independent variable and y is the dependent variable. So, for which we are having trying to get a Boolean relationship, okay. So, CBA 0 1 and BA is 0 0 0 1 1 1 and 1 0. So, we just put it 0 1 0 0 0 1 0 0, okay, 1 1 0 1 1 1 0 1, right, and then we write the Karnaugh map equation, right. So, B prime A C B prime plus C A, So, this is the combinatorial logic that we will get, right. So, how then the circuit will be made? So, clock will be given which is generating the sequence, right, to a that clock goes to a mod 8 counter, right. So, that has got 3 states C, B, A, right, which is now fed to the combinatorial logic. Within this combinatorial logic box, you have got this equation, right. So, basically these you can take in complemented output of if it is available or inverter and then AND gate and OR gate, okay. Together we will get it, and this is finally Y. Is it fine? Right. As I said, if it is mod 16, then we have to have 4-bit counter. Any other depending on the counting sequence. So, if it is 12-bit the sequence sequence we want to generate repetitively, so it will be a mod 12 counter, right. So, that is the way we have to move. Okay. And another example with which we end today's class is that what you see over here is 8 to 1 multiplexer. Okay. Again, this example can be extended for 16 to 1 and other cases. And this 8 to 1 multiplexer will be having 3 select inputs, right, and multiplexer does what? Many to 1. So, depending on select inputs, one of the input get connected to the output, isn't it? So, that is the idea. So, if you place 0 0 0, D naught will be connected, right. So, with 0 0 0 over here, right, D naught and Y is connected. The rest of the things are not contributing to the Y. So, that is the way multiplexer works, right. Now, you consider this input is selection inputs are fed from the from a mod 8 counter, right, which is your CBA, the CBA that you have seen here, okay, and a clock is fed to this counter. So, 0 0 0 0 0 1 and so on and so forth. So, this is the clock, right, right. So, when the clock is giving a count say 0 0 0, the first count, first clock, right. So, then D naught, whatever is the D naught value, that will go over here, right. Next is 0 0 1, whatever is the D1 value, that will go here. If D1 value is 0, it will go as 0. Next clock 0 1 0, whatever is the D2 value, okay. If it is 0, it will remain 0. So, then 1 1 1, D7 will go here, again 0 0 0, D naught will come over here. Is it clear? This is understood. So, this parallel set of data now is placed serially in a consecutive clock period, right, by this arrangement. Okay. Now, if somebody reads this one, this Y, okay, in synchronized with this clock and this count value that is there. So, when this value is 0 0 0 in the first clock cycle, it will he will read D naught, then he will read D1. So, this is D naught read, this is D1 read, this is D2 read, and this is D3 read, and so on and so forth, and then D7. So, what was parallel, now you can see it is in serial manner, you are able to read it, and it is time multiplex, means it is appearing in different point of time. So, this is one full 8 clock cycle, okay, within which this is getting read. Okay. So, this is in a way you can say it is a parallel to serial conversion is happening, and the data is able to be read through a time multiplex manner. So, this is another interesting example of using mod 8 counter in combination with a multiplexer. So, if it is a 16 to 1, 16 such parallel data to be read by one output line in different point of time, then this will be a 16 to 1 multiplexer, and then it will be a mod 16 counter, isn't it. So, you just need an extension of that. So, with this we come to the conclusion. So, what we have understood is that sequential logic circuit design concept can be applied to synchronous counter design for different modulo numbers, and such design can avoid the glitch which otherwise is seen for asynchronous reset based counter design. Okay. Lockout is possible when unused states are not considered and the counter remaining trapped in that. Okay. So, it is better to avoid it by explicitly considering it in the design steps. And of course, JK flip flop, T flip flop we have seen before, and also SL flip flop for counter design, but we have also we know that D flip flop also can be used, right, for design, and the corresponding excitation table can be used for the design process. Okay. And counters can have various other applications, the one that we had seen, that parallel to serial conversion, okay, used together with a multiplexer, or sequence generation where a combinatorial logic was used in addition. Okay. So, with this we conclude. Thank you.